Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 60, is the last class of this course. So, today we actually discuss about the what we have learned through this the journey of last 30 hours class. Okay. And one by one we pick a topic and we are going to discuss what we learned, then what is the takeoff of this, and then what I can provide for all topics okay, after this. And this is the keyword that you have to use to get this lecture. Okay. In topic 1, we discuss about the basic structure of the panel method. Right. Before that we have done bit of sea keeping, we have done bit of hydrodynamics, but the idea is to discuss that what is the panel method or lower order panel method. And if you remember, we solve one problem, that infinite radiation problem, and then we integrate this boundary integral equation as phi p is equal to over the surface of the body, and then we solve the source dipole panel method, which is del phi del n minus phi n into g over del s. So, we have used this boundary integral equation and we learn how we can split this boundary integral equation in the system of algebraic equation. Now, why we are doing it? We are using that one point Gauss quadrature rule, right, one point Gauss quadrature rule. Now, why this is saying this is important? Because here we assume these panels are sufficiently small, number 1, and also we are considering that G is very simplified 1 upon R, right. So, through this exercise what we learn is how I can split any surface, with a series of small panels, and also we learn how we can distribute the phi each panel, and then how I can write the integral equation into the summation form, like I equal to 1 to n and into this into dsi. In this summation form, how we are going to write this, and then we come to a matrix where we can say it is the matrix A into phi, then is equal to some known quantities at B, and how I solve this phi, and then how I calculate the added mass in the infinite fluid domain. So, this is what actually we discuss, and while doing this we also learn how to compute few geometric parameter through paneling, right. To do that we have to do so many things, right. Suppose I have this surface and then I am doing this paneling. Now, through this panel we learn that how I could get so many parameter, like for example, how I calculate this parameter C33, it means how I could get this value, the water plane area, so many things, how I can get that weighted surface, how I can pick the normal, right, how I can calculate the area of a panel. So, those things we discuss, and then finally we write a code, right. We write a code of course, in using probably C#, which calculates the added mass of a body. We discuss so many things, how we can do the paneling, systematical paneling using, like if you remember that we know that how we write the paneling, right, how I write the node first, and then we write the total node number, then 1, then we put this x y z value, and after that we write that element, and in element let us see take element 2, and then with that I write connectivity 4 5. In that way we just right, we know that how systematically I can write I can do the meshing, right. So, here then after that we write a code in C sharp. However, in MATLAB we actually come up with a the meshing engine, right. Here we are coming with the mesh engine. Right. So therefore, we have a MATLAB code. Now, in MATLAB code what it is doing? Suppose I have a series of data, or so that means I have some station versus z, and then if I have this offset table. So, if you giving me the offset table, from this offset table I can get the mesh for the to calculate this added mass damping for the body. So, if you give a offset table, it can convert to the mesh. So, that thing actually we done. So, here what I am giving to my students who is appearing for the exam and all. So, I am going to give this C sharp code to you. So, for your practice, like, and then I hope that you are taking the basic thing and you can go forward about it. You further develop the code, and then maybe you can use it in for the free surface. I have done for the infinite fluid domain. You can incorporate the free surface effect, and you can write a code for this. Also, I can give you this that MATLAB software. That MATLAB, it's a academic software. I just try to get some app so that I can provide you that app, so that at least you do not have to worry about the meshing if you have this offset table. And in fact, that offset table, in fact, you can generate from that same MATLAB code, right. So, this is the all about of the topic 1, right. Now, let us see what we learn at topic 2. Now, all are interrelated. In topic 2, we are finding out that lower order panel method order panel method for floating body. Right. Now, here we learn the basics of the lower order panel method, right. And and then how we can get the added mass damping, force, displacement, everything using this lower order panel method. Also, we discussed that what are the that key things we need to look for, like how we can do the mesh, right. If it is a bad mesh or good mesh, that we discussed, right. That means here we discuss that we should avoid a very bad paneling like this, right. Any quadratic panel with very high aspect ratios, or some very elongated panel. So, we know that we should not do all such panels. Now, if you get this such kind of panel, then how to handle it, that also we discuss, right. And also we discuss that how to get the data from any commercial software, like how to input the data. So, we have taken one example, we are using that WAMIT software, and we discuss that in WAMIT, if you are using WAMIT, then how to give the input, right, and then how to get the how to see the output. We do not have the WAMIT to run and show you the things, but at least we know that So that if you work somewhere where the vomit is available, you do not have any trouble to working on vomit. And also what we discussed, the basic principle of the potential theory, right, how I get the radiation force, how I get the added mass, how I split the phi into the number of components, like it is a I is equal to 1 to 6 phi I plus phi I plus phi d. So how we split the total component into the summation of different phi's, and each phi represents some part of the physics, right. For example, R represent the radiation part, I represent the incident wave, D is the diffraction potential. So therefore, the phi should be the total potential, and then we understand about the linearity. Also here we discuss about the Green's function G, which is a collection of Z0 and then GF. We did not talk much about this because it is fairly complicated and very mathematical to find out. So, we did not touch much on the free surface Green's function, right. However, we discuss about the G0, which is the Rankine panel method, and we discussed that how the different technique that we are following, like how to integrate it is in 1 point Gauss quadrature, then 2 point Gauss quadrature, where to apply the the analytic part, right. And also we discuss the analytic part of the Green's function. So, I expect from this topic too, you should know the following. Number one, that you should know about the how about the meshing. So, number two, about the how to integrate the Rankine part of the Green's function, then how to extract the data from the vomit result and how to give the input to the vomit results. So, all these things, and suppose if you have some kind of difficulty, like the program is not running, then to judge that why this program is not running, then how, what parameter you should change which influence that instability, that also we discuss in this topic too, right. So here only, I mean, that thing that from the coding aspect, one thing actually I did not give, but definitely you can do by your own, that how to do the analytic solution, right. So, this analytic solution of G0, this is the some coding thing that actually you can get from this topic too. Now, if I look at the topic 3, which is the IRF based solution. The IRF solution. So, here what we learn is, suppose I have the frequency domain data for added mass, if I have the frequency data for damping, if I have the frequency data for exciting force, and I also have the frequency domain data for the phase. Now, if I have this data, then how I can write the equivalent time domain code, right. So, here actually the first time we are writing a time domain code, but now it is not fully independent. This is depends on the frequency domain data. Suppose you have the vomit with you, and then if you add this data, then how to convert the frequency domain code to the time domain code, right. Now, here we discuss very thoroughly about the the each aspect of this IRF based solution. We discuss that how to get that value A infinity, right. Also, we discuss how to get this the b tau, that thing, and how I can solve the equation of motion m x double dot equal to f in the time domain. So, these three are the main key part of this whole thing. And also we discussed that why it is important to have the time domain code where the frequency domain code is not sufficient, right. So, in fact, at that moment we have not yet we did not do the direct application, because we are not ready at that point. But if you remember, then when we discuss about the, I think it is lecture 58, that time we are using that, we are modeling the green water load, right, and that actually I apply in the IRF based solution. So, at the end actually I showed you that where is the use of everything, where is the practical use of the IRF based solution. Sometimes that I avoid to discuss very detailed mathematical analysis, I try to go in a surface level. I put more emphasis on the coding part, right. So, now at least after the topic 3, everybody should have a impulse response based code with you. Now, what actually I am thinking of offering you a MATLAB code of the same thing, in fact for the rigid body, not the flexible body. So, I just I'll provide you the MATLAB code, and with some some data that I have with me, so that you can run this code and then you can incorporate a green water load on that, and you can see that how it is working, and then how actually the code is written. So, this is once you appear the exam and all, after that definitely this is the thing that actually I am going to give to my students. Okay. So, then we have the topic 4. Now, this topic 4 is the most difficult part, the topic 4 and topic 5, like we have the strip theory. In the strip theory, we learn that that how we can convert a 2-dimensional problem into the 3-dimensional problem, right. And then we learn that how to use the some chart like least curve to get the added mass, to get the damping, and then once we know the added mass and damping in the 0 speed, then how we can incorporate those data to estimate the response for the forward speed, right. So, those things thoroughly we discussed. Some coding aspect also we discussed, and if I remember correctly, I asked you to write a strip theory code assuming that this added mass data, I mean assuming following things, this wave heading angle, that beta equal to 180 degree, so that you can approximate the exciting force, I mean F exciting force you can approximate, because you can have you can approximate that the diffraction force, right. I mean this diffraction force you can write in terms of added mass and the damping, right. So, I know that we discussed this part, and I ask you, I gave you one homework where I ask you to develop a strip theory code assuming the simplistic head waves and as well as the exciting force, the diffraction in writing in terms of added mass and damping, and this added mass and damping you can get from uh, the Lewis curve, right. Also if you remember, we discuss about how simplified way we can write the exciting force also. If you remember that extra buoyancy force, we discussed that suppose this is the ship, and then if you superimpose the wave, and then because of this wave, let me just do that. Yeah. So, then So, then this extra buoyancy force can be act as a exciting force. So, that also we discuss, and extra and then moment because of this extra buoyancy force, that also we can take as a exciting moment, right. And then you get this added mass and damping from the Lewis curve, and then find out what is the strip, I mean just write a strip theory code. So, that also we discuss, right. So, now if you able to write a code, so now in this topic 4 you should send me that your coding, okay. So that I know that, okay, at least you know how can I write a strip theory code simplifying those aspects. So, now it is your turn to give me a software or some code in MATLAB or whatever the I mean maybe Python, C# that you are comfortable with, send me. Now, in topic 5, as I just said, it is the time domain panel method, right. So, now in this time domain panel method, I do it for the rigid body. And also we discuss how this extend to the flexible body, right. Not only that, here also we discuss some semi analytic method. Also here we discuss how to incorporate in some very easy way at least the green water load or the slamming load. So, in topic 5 I combined everything in this topic 5. I mean it could be break up into topic 5, 6, 7, I mean easily can, but okay, let it, because it is everything comes under the primary code is the time domain panel method code. Now, in time domain panel method code, like we discussed the basic principle. Now, when we discuss this, already it is known that about the paneling, about the integration of the Green's function. However, some complex part of this code we discussed that how we can integrate the convolution term, which is the I would say the most difficult thing in this entire code. Okay. Also we discussed that some sort of non-linearity, right. Till now we discuss everything under the linear regime. Only in topic 5 we discuss about the non-linearity, how we can incorporate the non-linear forces, right. And also as I promised, definitely I am going to give you that evaluation of the Green's function. Now, we discuss about the code, how to write that code, but we did not discuss about the Green's function, which is the most critical part. So, today I can tell you that the Green's function, that evaluation of the Green's function, that the free surface Green's function, of course, GF evaluation of the free surface Green's function, that MATLAB code I am going to give you. Okay. But you know why I am giving you, the idea is that you should be able to develop the remaining code at least for the rigid body case, because each aspect actually discussed throughout this journey. We discuss how to panel it, we discuss how to get this hydrostatic coefficients, we discuss how to write the algebraic equation from the integral equation, how to split the thing, everything actually it is very thoroughly discussed throughout this course. So, I hope that with getting this Green's function evaluation, the Green's integration of the Green's function thing, you can able to write this code. Okay. So, now let me summarizing that what the software or the program I am offering you. the first thing that now I already listed out for the first thing, yes, the C# code uh, for this infinite fluid domain, right. And also with this I'm going to give you that MATLAB software which makes the paneling, to make paneling, to make panels. Then I will just give the MATLAB code for your IRA based solution, right. And then I am just going to give you a MATLAB code for the Green's functions, right. So, in a way you are going to get some software that would be useful for you if you are working in an industry, or you are a research student, try to make your career in the domain of fluid structure interaction. So, if you are keen on these things, then definitely that what actually I am offering will be helpful for you for your future. So, with this note I would like to say thank you and all the best. Okay. Thank you very much.